Hello, my name is Juan Nicolas Paredes, and in this video I will make a general summary of what I saw in the third unit of chemistry. So to begin, I will make a short introduction to each of these topics. Ideal gases are hypothetical or theoretical gases, that is to say, like imaginary, which will be composed of particles moving randomly and without interacting with each other. It is a useful concept for the use of statistical mechanics through a simplified equation of a state known as the ideal gas law. Many of the real gases known in chemistry behave at ambient temperature and pressure like an ideal gas, at least from a quantitative perspective. This allows them to be studied as ideal gases within certain reasonable parameters. However, the ideal gas model tends to fail as temperature and pressure conditions vary, because its intermolecular size and interactions are important under these conditions. However, this model is not suitable for heavy gases. Now, we already know that is what is an ideal gas, but what are the types of gases? Let's start. There are three types of ideal gases according to the type of physical focus chosen for your approach. The first one is the Maxwell-Boltzmann ideal gas. Well, it is classified into classical thermodynamic ideal gas and quantum ideal gas, depending on the physical approach applied in its study. And the second one is the Bose quantum ideal gas, composed of bosons. And the third and last one is the Fermi quantum ideal gas, and that is basically composed of fermions. Now, how is an ideal gas defined? How is an ideal gas identified? Well, an ideal gas, as we have said, is a substance in a gaseous state whose particles are kept in a stable number without electromagnetic effects. Its kinetic energy is directly proportional to temperature. The collisions between the molecules that compose it with each other and with container are elastic, conserving momentum and kinetic energy. Real gases approach this ideal behavior only at ambient temperature and pressure when it comes to monatomic gases. But hey, is there a formula that allows us to calculate an ideal gas in a situation in which we needed it? Actually, there are multiple, and then I will explain each of them. The state of a quantity of gaseous matter is formulated based on four different variables: pressure, volume, temperature, and number of moles of gas. The ideal mathematical relationship between these factors is precisely the ideal gas law, which predicts the behavior of most real gases at ambient temperature and pressure. This law allows one of the four variables to be calculated from the knowledge of the other three, according to the formula that is expressed like P by B is equal to N by R by T. P represents the pressure of the gas, B is volume, and the number of moles of gas, which must remain constant, R the constant of the gases, and T the temperature of the gas in question. If a gas complies with this law, it can be treated as if it were ideal. This law is also the combination of the laws of Boyle, Gay-Lussac, Charles, and Avogadro. The first one is the Boyle's law. In the 17th century, the scientist Robert Boyle carried out a series of experiments using gases and liquids, thanks to which he determined the effect that pressure exerts on the volume in gases. This led him to formulate his law, which states that the volume of gas varies inversely proportional to the pressure if the temperature remains constant. This is formulated for ideal gas as follows: P1 by V1 is equal to P2 by V2, where variables with 1 are initial and variables with 2 are final. The second one is Gay-Lussac law. This law explains that the pressure of a gas of mass of gas whose volume remains constant is directly proportional to its temperature. For ideal gases, it is formulated as follows: P1 divided into T1 is equal to P2 divided into T2, where variables with 1 are initial and variables with 2 are final. This formulation was raised by Joseph Louis Gay-Lussac in 1808. The third one is the Charles law. Thanks to the studies of this Frenchman Jacques Charles in 1787, we have this law that expresses the constant relationship between the temperature and the volume of a gas when the temperature is constant. This is formulated for ideal gas purposes as V1 divided into T1 equal to V2 divided into T2. Well, the last one in Avogadro's law, which was formulated into 1811 by Amadeo Avogadro, who discovered that under equal equations of pressure and temperature, the relative densities of a gaseous bodies are proportional to their atomic numbers. His basic hypothesis is that equal volumes of different gaseous substance under identical condition of pressure and temperature will contain the same number of particles, molecules or atoms. The general gas law or combined laws, it says that a mass of gas occupies a volume that is determined by the pressure and temperature of a gas. Study the behavior of a certain mass of gas if none of these quantities remains constant. This law is used for all those ideal gases in which the volume, pressure, and temperature are not constant. And in addition, this mass does not vary. The formula of this law is expressed as seen in the image. That is, the volume of the initial situation times the original pressure over the temperature is equal to the final volumes times the new pressure applied over the modified temperature. The pressure is a force that is exerted by the surface on the object, and the smaller it is, the greater pressure there will be. From the combined law, we can calculate the way in which the volume or pressure or temperature change if the initial conditions, that is P, V, T, and are known to and two of the initial conditions are known, that is two of the three quantitative PT, VT, or TF. Let's do an example. A gas occupies 2,000 cubic centimeters with a pressure of 760 millimeters of mercury. Find the volume when its pressure changes to 1,600 millimeters of mercury. The data will be V1, that is 2,000 cubic centimeters, P1, that is actually 760 millimeters of mercury, P2, that is actually 1,600 millimeters of mercury. Well, the formula that we are going to use is the combined formula, that is P1 by B1, that is equal to P2 by B2. And we are going to actually calculate the volume number 2. Since V2 is multiplying, it bases dividing, and the formula becomes as you can see in the image. So if we calculate these digits with our calculator, we will realize that V2 is equal to 960 cubic centimeters in it's our final result. And yeah, knowing the variables that influence the ideal and real gases, we can talk about the relationship of the greenhouse effect with climate change, taking into account the different variables that produce it. Well, currently one of the great problems facing humanity is the fight against the increasing greenhouse gases. Normally we talk about carbon dioxide, but there are many more. Find out which are the most important cases, what effects they produce, and even the countries that emit the most emission into the atmosphere. The greenhouse effect is presented as one of the greatest consequences derived from the current climate crisis. The Organizations for the United Nations defines it as a phenomenon that produces an increase in the average temperature of the earth and of the water that covers it as a consequence of the accumulation of greenhouse gases in the atmosphere that retain solar radiations. However, many people wonder what are greenhouse gases or which are the most important. And next, I will explain about this. According to various organisms, greenhouse gases are those gaseous components present in the atmosphere that absorb and emit radiation at certain wavelengths of the spectrum of terrestrial radiation emitted by the Earth's surface. When sunlight hits Earth, the rays pass through the atmosphere and come into the contact with the surface. A part of these rays bounces off and is returned back to space, while another part is absorbed by the planet, heating it, to be later returned into the form of infrared rays. At the moment the greenhouse effects process begins, infrared rays have a longer wavelength than those that actually reach Earth, such as ultraviolet rays, and therefore produce greater agitation in some types of molecules. In this way, while those molecules responsible for these gases allow the ultraviolet rays from the sun to pass through, at the same time that they retain the infrared rays emitted by the planet, preventing excess heat from escaping from the Earth by being retained within them. Well, this effect has always existed on Earth, and it is what allows our planet to maintain a temperature suitable for life. However, since the beginning of industrial evolution in 1750, technological advances and fossil fuels led to the rise of the former, which led to uncontrolled emissions of greenhouse gases. Types of greenhouse gases can be classified between direct and indirect greenhouse gases. The direct ones are those gases that contribute to the greenhouse effect without undergoing modifications, that is, as they are created and expelled into the atmosphere. Within this group are carbon dioxide, methane, or nitrous oxide. The indirect, unlike direct, these gases undergo a transformation when they reach the atmosphere that converts them into the direct gases. Here they can be found as nitrogen oxides, volatile organic compounds other than methane and carbon monoxide. And well, as we know, water vapor is still the most abundant greenhouse gas in the atmosphere, and clouds are an important part of Earth's planetary greenhouse. Human activities are not directly affecting the global average concentration of water vapor. However, the radioactive forcing produced by the increase in the concentrations of other gases can indirectly affect the hydrological cycle. A warmer atmosphere tends to increase its water vapor content, which will affect cloud formations. So the conclusion of all of this is that first, an ideal gas or hypothetical gas allows for practical consideration that facilitates some mathematical calculations in which there is no attraction between its molecules, unlike a real gas in which there is attraction for collisions occur. The fundamental contribution of Boyle, Gay-Lussac, Charles, and Avogadro allow us to know the pressure, temperature, and volume of a body in a gaseous state, as it also facilitates the study today. The greenhouse effect is defined as the warming of Earth's atmosphere. Although for years this effect was discussed by scientists and politicians, today is an undeniable fact, and climate change demonstrated it. Another conclusion is this is a natural effect, and without it the temperature will be so low that no type of life could develop on Earth. And the last one is, at present, too many gases are being released into the atmosphere, such as carbon dioxide, generated mainly by the burning of fuels, which accelerate this effect. And well, basically, this will be it. And I hope that I had make you understand all the topics. And yeah, thank you for watching.